Okay, people, this should be a refresher from last year. We're going to be going through light as a wave, or wave behaviour of light, rather than the particle behaviour of light, which is coming a little bit later. So in this one we're going to talk about in-phase and out-of-phase wave sources. So these two are in phase, these two are out-of-phase. Perfectly in phase, perfectly out-of-phase. We're going to talk about incandescent light sources and why they're not coherent nor monochromatic, and we're going to use the principle of superposition to talk about constructive and destructive interference using this example over here again. So if we have two waves that are going to arrive in a place in phase or arrive in a place out of phase, what we're talking about is the phase of the wave at that particular point in time. So if these two light sources here arrived at the same place, so let's say they're both pointed at that spot there, they would, because they're doing the exact same thing at the exact same time as they're moving through space, they're going to arrive at this point here doing the same thing at the same time, which means that they are going to interfere with each other. Because they're vectors, they're either going to constructively interfere and build on top of each other, or destructively interfere and sort of cancel each other out to some respect. So what we're looking at is the point on the wave. So if we have peak meeting peak, then we're going to get constructive interference. If we have trough meeting trough, again, constructive interference. If we have peak meeting trough, destructive interference, trough meeting peak. You get the idea. So these two waves, when we add them together using the principle of superposition, they will interfere with each other. The wavelength won't change, but the amplitude will. So it will end up looking something like this. So the wavelength hasn't changed, but the amplitude of the wave is now hopefully about twice as big. Okay. If we add these two here together, we'll end up with absolutely nothing, because the amplitudes cancel each other out everywhere. So hopefully you can see, if this is the signal that we're trying to receive, we're going to receive a lot of it. Here we're going to receive absolutely nothing. So this is good for TV and radio, this quite bad. When we look at things like incandescent light sources, what we're looking at, what we're talking about is something that's glowing because it's hot. So you get your standard light globe, probably not really that standard anymore, but you have your light globe like this, and your light globe actually has an incredibly thin filament inside of it, and when you pass electricity through a thin wire, it heats up. When it heats up enough, it's going to start glowing. So the trick with these sorts of things is to make the filament hot enough so that the charged particles inside it vibrate backwards and forwards really quickly. So it's not just the electrons, it's the nucleus as well, and you end up with a whole bunch of red, orange, yellow, green, blue, indigo, violet light. You'll also have some ultraviolet down here. That's the stuff that will give you suntan, and you have the infrared over here. In an incandescent light globe, there's lots of that. That's the warmth or the temperatures you can feel from the surface. So because we have charged particles vibrating backwards and forwards, they're all doing it randomly. So the frequency is going to be reasonably random to a degree. So once we get into this, the filament hot enough so it's somewhere in this visible spectrum, we'll have some of them vibrating at a frequency that will give off red light, some of them somewhere in the greens, somewhere down here, and the hotter the globe gets, the more you'll have towards the blue end of the spectrum. But because it's random, we have different colours. And if we have different colours, we're not monochromatic. So mono meaning one, chromatic meaning colour. We can't have monochromatic light. Similarly, if we have all of these particles vibrating in at random speeds and all in random directions, what we're going to have is all of these things heading off in different directions. If they're moving in different directions, they aren't coherent, because coherent means that something's moving along with a constant phase relationship. So, like I've drawn on the board before, so over here, we have these two waves that are in phase, they're always in phase, they're maintaining that constant phase relationship, therefore they're coherent. These two here, perfectly out of phase, but they're always out of phase, so they're maintaining that out of phaseness, so they're also maintaining a constant phase relationship. But if we have different frequencies and different colours, and we have different directions, then we're going to have stuff that's got wavelengths like this, and we're going to have stuff that's got wavelengths like this, and we're going to have stuff that's got wavelengths like this. They're all different, so they can't maintain constant phase relationships, because even though they might have peaks that are reasonably close, their troughs at the other end are miles apart. Okay, so in order to be coherent, it needs to be going in the same direction, maintaining a phase relationship, and if it's different colours, different frequencies, just can't do any of those things. So using the principle of superposition, so vector addition, we can analyse wave fronts as they travel through air and meet at a point. So we'll use the diffraction gratings, we'll use Young's double slit experiment to show light behaving like a wave using this phenomena here.